Well, topic of the fourth session is digitalization in railway track. The first speech is by Marco Acquati, that I invite on the podium. He will speak about the risk-based approach in design of slab track for vibration mitigation. Please, Marco Acquati of Metropolitana Milanese Milan, Vibroacoustic Project Coordinator. Se vuoi stare in piedi, sì, sì.
Thank you for the introduction. Good afternoon. I'm here. Well, the session is about digitalization, but my presentation is not really related to this topic. I'm here as a risk management professional, as well as a track expert, as well as a vibroacoustic expert, and that's enough. And I got a special certification in risk management, and this is one of the reasons why I'm here, because I wish to make you understand why risk management could be a good approach for any problem that may arise in truck design, installation, and management. And risk management is a process, a methodology, a well-thought practice, well-defined and applied in many fields. I'm here to let you understand, to bring you by hand in this very, very interesting field, to let you understand that maybe this technology can help, this methodology can help your technology and the benefits that may arise. Ahead of this presentation, I had some conversations with some of you, some of the experts here, because I wanted to understand whether this methodology can help really your daily work, your daily life. And I received a very good feedback on this. So I'm just really going ahead with the presentation. So let's have a look about what risk management is. I'm going to show you with a very short video. I just invite you to watch this video mindfully, and I invite you to understand how this process illustrated by the video can be applied to your work and to your technologies. So this video is showing the various steps of risk management. The first step is to detect the risk, how high is it, and how risky is it. So the second question is, can I afford it? So the next step, can you see it, is to use a response strategy. And the response strategy, if you can see, is to use the pillars. Okay, and how many pillars can I use in order to eliminate the risk? And in this case, you see that at the end of his job, he used all the pillars available, and he decided to just looking around to see whether there could be other strategies to be used, other tools to be used. So the question applied to our field is there any risk related to the design phase? Is there any risk related to the installation phase? Is there any risk related during the service, the operation and maintenance? So we heard many applications during the previous presentation showing that some risks are considered. And also I'm really pleased to say that just before my presentation, there was a presentation by Jens Kleber just showing that some risks were considered during the design phase of his solutions. So For other example, we can talk about the risks that may happen after a derailment, like Thomas showed before during the presentation by LVT. So I wish to bring you progressively into this topic. Maybe you all have a risk management office in your company, but have you ever thought that risk management is something that can be thoughtfully applied to your processes and to any aspect of the truck design, any aspect of the truck installation, any aspect of the truck maintenance? And it can be applied since the very first formulation of a truck system, from the beginning to the end, including also the final disposal of any component of the truck system, during the whole life cycle of the system. And the concept of risk is strictly related to value. I remember a presentation, I don't remember who was, a presentation showing, yes, Ruben by Pandol, showed a slide where where there was a formula to calculate the value of the truck system. Well, within the truck system also the risks should be considered, because the risks are actually, the concept of risk is so strictly related to value, to the concept of value, to the point that we may say that any negative impact risks are anti-value. So even negative impact risks should be considered to evaluate the value of the product that is delivered by your company. So I'm here to let you understand that risk management is a way to bring value to your company. Let's have a look at some definition. So the first definition is about what are the main steps of risk management. The first step is to identify all the risks. Are we aware that we have identified all the risks associated to our technology, to our truck system, to our fastening system, to our sleepers? This is not an easy job, not at all, but it must be done. The second point is that identifying risk is not the only one, but it is necessary to analyze the risk. How big is the risk? How can I manage it? Can I afford it? Do I have the tools to face that risk? And the third point, in this very important point, in this definition, is that this should be done throughout the life cycle of the product. Throughout the life cycle of the product, so from the cradle to the grave, throughout the expected life of the product. The second definition is again important, because it is saying that the risk management is the practice of developing a collective understanding among stakeholders to anticipate and manage issues. So risk management is a collaborative job. It is not done just by one aspect. It is important to get in touch with all the stakeholders. I should include in the stakeholders also the contractors, the people who are in contact for the installation of the truck, the operators, and also potentially the receivers, the people who are somehow impacted by the vibrations that are generated close to the truck. And I want you to bring attention to this, to what is the second part of this definition. It fosters proactive implementation of lower cost preventive actions compared to higher cost reaction, and increases opportunities for business benefits. So in other words, application of risk management means saving money, having higher incomes, having higher revenues. This is the benefit, the main benefit of the application of risk management in your processes, in your daily work. let's move to a more operative point. So the risk register is the first step for risk management. Risk register is a table showing the list of all the potential risks. This is just an example. And in the risk register, one must consider the effect of the likelihood of the risk and the potential impact of the risk. The risk score is the product of the likelihood times the impact. Then the second step is the response strategy. What shall I do in case the risk happens? What shall I do in case, for example, a train derails upon the track system and the part of the track system is damaged, like Thomas exemplified before? Okay, but risk management means to consider this in advance, properly in advance. As said, it is a proactive approach. As said before, it is a proactive implementation of the solution. I don't have to spend money, it is said here, in reactions which are typically with higher cost compared to a proactive approach. And the response strategy means really to understand in detail what can I do, what I can do to give a good response to the risk and to limit an increase of cost. This brings to another important point, that is the cost management. The cost management must be evaluated to understand how it may change after the implementation of the risk response. So previously, before the cost management, I have a certain evaluation of cost associated to the risks. After the application of the risk response strategy, I have a different cost. And I can understand that a risk mitigation is good if it helps to save money, time, and resources. This is the result of this operation. I defined a post-impact risk score, and according to this post-impact risk score, I define a residual economic monetary value. So you can understand with a very short explanation. Well, of course, I can spend a lot of money to speak to you about risk management, but you can understand that risk management is a process to evaluate thoroughly any situation, any scenario we may encounter, and proactively assume what is better. Really proactively assume what is better for the situations we may encounter. So in this way, we can understand that every track system, every floating slab, every block, every sleeper, every elastomer, every fastening system is not considered in terms of good performance, generally speaking. It must be considered in terms of its potentiality to give rise to risks, and its inner strength and its inner associated strategy to reduce, to remove, to mitigate that risk. In other words, risk management could be a good approach in order to select the best track system for a particular application. It is important to understand, but probably you are all aware of this, that the best track system ever does not exist. The best, I repeat it, the best track system ever does not exist. But probably it does not exist even for a particular application. It is important instead to understand that it exists the track system whose associated risks are more easily manageable. It exists the sleeper whose associated risks are more easily manageable. It exists the elastomer whose associated risks are more manageable. This is the way risk management is the best approach to define a good solution for some kind of applications, because it doesn't look at the system as a whole, but it looks at the system from the effect of the system. So, these are just some examples to use risk management in order to decide to define which option is optimal. Let's assume you have different track solutions, different track systems, among which you are required to make a choice. Okay, and risk management can provide the results in order to make the comparison. For example, we can make comparison on the total contingency reserve. These parameters represent the total amount of funds set aside to address identified risks. So, the system whose total contingency reserve is lower is the best system, is the optimal system. Other example is total number of risks exceeding a certain impact factor. This parameter helps in understanding the severity and frequency of high impact risks. Okay, so again, this is a tool to select the best solution, because the best solution is the one whose risks are low in number. Let's move on. Just want to say some other words about this approach. So risk management is, in my opinion, is the fuel to your management strategy. Risk management is really something that can bring a boost to your production management, to your installation management, to your maintenance management related to the track. And you can understand also that risk management is not like gambling. These are not these ones are not random numbers without meaning. This is really some kind of fascinating science. Okay, let's move on with just a couple of examples related to vibration. So the application of risk management to some particular situation of vibration mitigation. So everybody here knows probably that if you have to design a floating slab track, you have to consider the floating slab track as a single degree freedom system, okay? So with a resonance frequency, okay, this is the response, this is the frequency, and this is the resonance frequency. And in order to have it really effective, it is important to have this resonance frequency as low as possible, okay? Is it clear? I suppose that this is understood by everybody. And if this resonance frequency is low, the mitigation is given by this green area. The wider this green area, the better is the mitigation of vibration, okay? Because this is the response, so this is below 1, and it means that there is a mitigation. But what happens if you have some needs, and this is a risk, some needs related to maintenance? Okay, sometimes if you have some needs related to maintenance, I mean in particular to propensity to air corrugations, you are required to design a second resonance frequency. Typically, air corrugations are governed by the fastening system, or in general, the part of the track system very close to the rail, okay? And this introduces a second resonance frequency. And can you see what happened? So you see that there is a second resonance frequency, and this second resonance frequency is cut away, a significant part of the mitigation achieved. So on one side, you have a good performance of the floating slab track. On the other side, you have to satisfy, to comply with another need, and the other need implies a risk. So the risk is that you have, for sure, a better, a lower propensity to air corrugations, but you reduce the mitigation you can get. The second example I wish to bring to your attention is human sensitivity to vibrations. Okay, you know, again, you probably all know that there is no absolute threshold for human vibration sensitivity. Okay, so there is just a correlation between vibration level and human response. And this is, no, sorry. And this is the correlation, okay? So you see here, there is the vibration level, and here, the percentage of highly annoyed people by that vibration level. In other words, it means that, for example, if we assume a limit widely used in Northern Europe that is 3.6 millimeter per square second, so this limit is around here, okay? And this limit in Northern Europe means that this is the limit for Class A residential areas, I read it, which means very good vibration conditions in which exposed people will only exceptionally be able to notice vibration. Okay, I finished the time? Ah, okay. just close the presentation. And so, with this diagram, you can understand that at this level, 3.6, okay, you have 15% approximately of people disturbed, okay? But with this diagram, you can understand also that the people responsible for carrying out the track works may decide that even if the value remains around 10 millimeter per square second, that is 25% of disturbed people, the risk of residents feeling significantly disturbed is low compared to the relatively low economic impact, and may decide to implement an initial, so something that is not as good as 3.6 or something higher, an initial inexpensive, relatively effective measure, and assess whether this alone is sufficient to achieve a good level of satisfaction for the people. And this happened. For example, in Milano, we applied not this very low level, but a higher one, something around 10. So in theory, 25% of people could complain for the vibration, but nobody complained, because this is just a statistical value. So this is a typical example of risk-evaluated approach in order to limit the money expended and to achieve, in any case, a good result. And thank you very much for your attention, and that's all.
Thank you, Marco. So I invite Giuseppe Bomben, Sales Manager, Automotive Diagnostic Solutions. He will speak about 360 degrees no contact survey for railway and underground environment.
Yes,
thanks.
You. Very interesting presentation before, because it talks about risk and actually monitoring the risk. You need to monitor them. In fact, we care about the diagnostic of especially railways, on slab, on ballast, on whatever. Few words from where I come from. DTS is a company in the northeast of Italy, nearby Venice, and we produce tools for the diagnostic on railways. That this kind of work needs several achievements in terms of mechanics, electronics, and then computer science. Lately, also artificial intelligence, and we needed to adapt to the real owner of the diagnostic equipment, that is who belongs to the trucks, to the railway convoy that has to be installed at the systems. So we needed to have a few peculiar knowledge all around in order to fit the requirements, to fit the railway requirements as well, and to fit also the physics, that it is something you cannot argue with, you know. We have a bunch of systems for monitoring all around the railways. We will focus today, of course, on the track imaging. That is the main focus of today. And if we have time, we just give a glance to the tunnel scan as well. But like a colleague before talked about railways, there is also a matter of steel. So you have also the rail corrugation and rail profile measuring systems. Anyway, go back to the track imaging. This is a kind of equipment for having high-resolution images of the track, up to 0.5 millimeter. Yeah. For example, just the top of the rail. And so we go to the steel aspect. But then you can have a look, like we have here, a picture of the wall around, surrounding of the rail. So you can use a less resolution images, like 1 millimeter per pixel. In short, like somebody talked about Lego today, the Lego blocks and so on, we have such a kind of a same solution. You have different kind of models, and for, that's the one, okay. This is just for the top of the rail, then this for the, let's say, the surrounding with fasteners. And then you have the fastener as well with also the 3D reconstruction with the laser scan profile. And then you can fit them in several configurations in order to target what you look for, what you are interested for, of course. So here you have a glance of what can be the most complete one, where you have the full track imaging, and you have also the 3D reconstruction, like top view. So you can have a really deep understanding of what is going on track. And after the acquisition, then becomes a matter of decide what is good, what is not good, what is a little bit in the middle. So for who comes from computer science and says, okay, you have a model, and with a model you have 100% sure of what you are going on. Is not what you can use, there is not a model for the number of defects you can find on fastener, on rail, fish beds, and sleepers, and so on. So you have to rely on AI. AI is statistics. So don't ask for the 100%, you will never get it. And also this introduces another aspect, that it is a matter of continuous learning. So in short, the AI has to be taught on what to look for. And this can be done by giving a number of examples of it. So we had to learn how to do that, and we have a software that can grab all the kind of imaging data that we can acquire from our system, and then we process them. We process because unless there is no way to do it by manually, let's say, so we have to pass through a software that can decide what is good, what is bad. What is the path, general path? I mean, we start from the acquisition, from the track. Then the data can be on the train as well, but usually it is transferred to office, where it is elaborated and you get the report. The report is the half of the work, because it is really important. Each customer has its own peculiar needs, so you have to make the report like they want. And for customer, I'm talking about the final users, the railways in short. In the middle, what do you have? You see, this is this never-ending learning story. That you have the expert of the track, of that track, because the expert of Copenhagen has a different idea of the expert of Taipei. And so it can give you some feedback on what is happy about and what not. And then you can, the owner of the AI has to increase the AI knowledge of the data set, and then it can update 2 times a year, for example, the AI engine in order to get better results. This is quite important to keep in mind that it is not build and forget and never, and nothing also drop and forget, but it is continue working over. Okay, now we have the very quick video. This is the company video, and just to keep in mind that first of all, it is the kind of environment that we are supposed to work, and we have to adapt to it, especially because each customer has its own need on that. And then we need also to consider the kind of vehicle that are available for maintenance. This is why we made such modular construction elements in order to be fitted on the vehicle. Then the software managing can focus on each aspect of the rail and the track as well, in order to grab what are the most important. I mean, not everyone wants everything. They can just focus on one single aspect. And we have to be ready for, especially for the report part, because for the reports, we need to focus on the kind of results that the customer is needing. Here we have an example of an AI installed for a slab track, and where the automatic recognition is working over, and it is used by the customer. Take the case, it is the 20-kilometer acquisition, then they have the reports, and they focus, okay, in which kilometer I'm supposed to bring my team for fixing over. And so they can focus and bring the team always in the worst path of the track. In this way, the full track is always monitored, and it is reported not in imaging, because operators, I can assure you, after half an hour, they don't see any more to the images. They just want to see the reports in order to focus on which part of the track they are interested more, and give an eye for the maintenance team. Moving a bit outside the track, as a slab track, it is most used inside, of course, metros, and metros are inside tunnels. So the same concept is applied to the tunnel as well. It is the same kind of camera with the same kind of lighting. The concept is once again the same. Here it is added a kind of geometry system, let's say. Geometry, I mean, we can call it more properly a shape system that give the profile of the tunnel inside with the image. Here we have a couple of images of two real installation on a track and on railways, and you can recognize this area that you see all around. It is the lighting element that gives the light just to the small slice of the world that is acquired by the cameras, that are linear scale cameras. And so it can be combined together with the 3D, let's say, 3D scanning of the environment, where you can grab also measures, quite important, inside tunnels. And from the image, once again, there is the same game of before, of training the AI in order to grab the information, especially about cracks, water, aggregate, pops out. Okay, very quickly, it is most of the aspects that the tunnel maintainers are interested about. Also, these are not linked to a model. This is quite difficult to do a model of a water leakage, you know. It belongs to the kind of concrete of the mountain that is behind, a number of aspects. So you have to use such statistics through the AI to have the automatic recognition of it. And this also is made by our own engine, because we understood that the most important aspect of that is linked on the data itself. So this all this work of acquisition system, elaboration system with AI for grabbing the kind of defects and so on is all part of what you say, the data for the so-called risk management, quite important. I mean, in this way you can have the data where you can rely your actions for preventive maintenance from tunnel as well for the truck. Well, for the tunnel, we have also a system based on thermal imaging that can increase the capability of the system, especially if the behavior is not visible, I mean on the visible wavelength, but goes on the infrared. And, and you can collect them all together on the same environment. On this aspect, the AI is very cool because it's able to grab data that can be nothing to do each other, but they can find correlation that human being can be really in trouble to get on that. So having this AI engine and feeding it, don't forget the feeding of the AI engine, it is the most important, oh, not most, but let's say the 50% of the difficulties on the AI use can let you to have always better in advance information about preventive maintenance. And the reports as well, like we made for the slab track, we have the reports as well, also for the tunnel, for the scanning element. The positive aspect for the tunnel is that it grabs information of the ceiling, like on the wall that you have, you can touch with your hand. Quite difficult without a normal equipment. It is difficult to go up to the ceiling, having a look at what it is over there. With this system, you are on the same page. With 1 millimeter per pixel, I can assure you, is like having the front of the wall at about half a meter from your eyes. The bunch of systems that we have installed, rail vehicles, railroad, Far East actually it is the predominant part. We have also something in Germany as well, but the Far East, it is where we have the vehicle with the most installed elements, especially this one has the full, you can recognize down here the slab track, not slab, the wall track acquisition system with also the tunnel system around. In this way, came out what I called before the 360 degrees all around system, grabbing imaging from where the training is passing through. Here we have a quick company video as well for the tunnel scan, where especially at the end, I will focus on one important aspect on the AI that we've done, that you have the possibility to choose the severity that you wanted to use, the threshold of the alarms. This is something not common on other competitors' solutions, that you can, instead having 1,000 of errors, you can tune the threshold down to the level that you can manage on the next maintenance activity. And so you can be sure that you are addressing your people to work on the worst position of the tunnel, as well as they made on the track before. Here we have the evidence of the 3D profiling around, in order you can measure even if you are going outside the limits that you can decide, of course. And what you see over there, it is like the snake skin of the tunnel. So you have the ceiling in the middle, and then top and down, you have the left side and the right side. Let's talk, yeah, I mean, you have the main are water leakage and cracks, and the material attachment. I mean, all the things, even if you have a new tunnel with something different, you can grab it. This is the part I mentioned before. It is the possibility, you see, to tune the severity that you are looking for. This was found quite useful from the operator in order that they can decide the threshold and go to target only the most severe part. Of course, once you have the full digitalization of the track and the tunnel, the operators can get skilled on tracing what is important, what is not, and in this way feeding the AI data set in order to get it always better and better, just not to forget about this always learning capability. At the end, the production, once again, it is the reports. Like I told you before, operators after half an hour, they don't see anymore about any picture, they just want reports in terms of positioning on the track and what it is needed to do. And yeah, I mean, I made also a too quick presentation maybe, but never mind. I guess that you will appreciate as well. In case if you have questions, of course, I'm here.
So now I invite Stefan Damm and Jochen Nowotny, respectively DMA and track machine connected companies. Their speech regards digital transformation of railway infrastructure. Thank you.
Thank you. Good afternoon. We are representing the digital and diagnostics branch of the Plaza Anteura Group. I'm Jochen Nowotny, CEO of Track Machines Connected, a Plaza Anteura company and sister company of DMA. And this is Stefan Damm, the CEO of DMA. So how do I switch further here? How do I go to the next page? Right here. We got it. So who is Track Machines Connected? We exist since 2019, and with 2 sites in Austria, 1 in India, and our focus, the focus of our around 100 people is to develop railway-dedicated software solutions for the railway market worldwide. Naturally, being Plaza Anteura, our focus are tamping machines and tamping. Nevertheless, we also developed some solutions which are focusing on the automation of manual inspection, and this is what we show today. But before we come to this, Stefan, who is DMA?
Yeah, who is DMA? Good afternoon, everyone. Warm welcome also from my side. Probably it's one of the nicest slots just before aperitivo. Who is DMA? Since 2023, DMA is 100% of Plaza Anteura Group. It's a company based in Turin, founded and based in Turin, Italy. But actually, we're taking the technology we're developing in Turin out to the global railway industry. That means we're doing it from Canada to New Zealand to Japan to all places of the world, especially where there is high-speed and highly used railway systems such as metros and so on.
Good. Now we come to the solutions, and allow me to use one phrase with 1,000 and no definition, digital twin. I'll show you ours. This is the first project we did in 2021, a railway line in Germany. And what we provide there are high-precision colored point clouds. I'll tell you why. But before that, some KPIs. What you see here, what we process here and provide are point clouds with 100 million points per kilometer of track, and we process 1,250 color images for 1 kilometer of track. Another project we did is this one. These are no images, these are all colored point clouds. Is for the Riedbahn in Germany, which some of you may know, which was the first major full general renovation project 2024 in Germany. It is a track between Frankfurt and Mannheim with 300 trains a day, and it was closed for entirely 5 months for full refurbishment. What we provided was the planning baseline for this project. So we do a one-stop shop. We are leveraging our measurement vehicle fleet, and we take the point cloud from the tracks, and we offer 2 different categories of precision. One is a GNSS-based precision, where we use GPS, the IMU based on the scanner system we are having. and calculate the trajectories out of this one. The even higher position, where also DMA comes into play, we take the track geometry, compensate any drift with external reference markers, put it then, the track geometry, to absolute track coordinates, and then align the point cloud onto this. With this, we have around 2 centimeters absolute accuracy. Well, what to do with this? You stop any manual inspection or any manual measurement of tracks before you do a construction. You don't close the tracks. We go there through normal traffic. You don't need any safety personnel on the tracks, and you cannot make mistakes, because if you get something to measure, you go back into the point cloud again and don't go back on tracks. And with this, we are economically even more efficient than any manual inspection. What the customer gets is an open data file, so LSZ format. There is no software or no log-in to our products. They get an open format. It's a service provided by us, and they can further process it within their AutoCAD, for example. And that was what actually was done here for this project I mentioned. But there is also something else I want to show you. Who knows somebody who likes doing the inventory? At least in my company, it's not the most favorite task, the counting down in the cellar of all your goods you're having. So we were deciding this, we are doing this for the railways. So we have the point cloud, and then our algorithms come into play. We use some algorithms, some edge detection, some pattern recognition, some AI-based recognition on the images, find an object in the images, go into the point cloud, because in the point cloud you can measure, you have the real data on it, and we produce the categories of such an object and put it into a database. You have around 1,000 object points per kilometer to be processed, so it's quite an effort. So doing this manually, doing the inventory, of course, is not a favorable task of people. And we do even more. Operators can give us their existing inventory data, PDF, CAD, drawings, whatever. We manually put them into the same database or separate database, and then you can run a diff between the two, and you got the change log and your actual inventory along the track. And with every run, you can renew it once you have digitalized it in this way. Again, all the data are open source. Customer can use it as they wish. This is the part of Track Machines Connected. Stefan, your solutions then.
Thank you, Jochen. Yeah, let's talk a bit about slab track in detail or in specific. There's 2 types of inspection which we offer for slab track. One is track geometry, and the other one is visual inspection, where we already learned a bit about beforehand. Slab track is actually the ideal track in order to a couple of measurements. We all know, and we heard before, that in slab track, there's much more stability compared to other types of track, but actually this increased stability compared to ballasted track, for example, that also lets us know a bit more detail about the changes that are happening. For example, changes that are happening where infrastructure changes from tunnel to open track, to stations, to bridges, and so on. So in this image, for example, we can see very nicely that most of the track over time, and you have all those lines over time, each color line in this image is a different timeline, basically, a different time of measurement. You see that it's all very parallel and that the deterioration of the track is very low. So the geometrical measures of the train remain quite stable. But there is one point where we actually see from the beginning of the timeline, and it's getting greater distances, the track is deteriorating, and the gauge, for example, in this case, is widening. And of course, this is a point where you can actually early in time work against. You have the prediction that actually shows you when the track would be too wide, but early in time, you can already work against this. So the prediction then shows you, or the current state of the track shows you a track quality index. In this case, of course, green is green, orange is like something in between, and there is no red categories in this track. But if you actually do the prediction over time and the extrapolation of the data over time, you can easily see in which place of the data, in which place of the network, for example, like here, you have a deviation from the standards, and you can also predict when the deviation will be as large that you need to change something. But what is more interesting about that is the root causing for these measurements. And that is why I actually have brought you two slab track inspection case studies, one from Eurotunnel and one from the Elizabeth line in London. When we look into the Eurotunnel infrastructure, we see that this is perfect for visual inspection. It's clean, it's covered, so we don't have any dirt in there, we don't have any influences from light in there, so this is just perfect for video and for automated video inspection. If we look a bit what can be done there, or let's have first a look at what it is. So it's 50 kilometers of railways. It's quite a short track. 8 kilometers running in open air, 50 kilometers running in tunnels. And we're doing the inspection there at 100 kilometers per hour. What is interesting is what happened actually in the first year of inspection, because there was a case, or there was an issue with the fasteners in this track. And in fact, in a 2-week inspection on those fasteners, we found about 600 new defects every other week. And what we are very proud of, actually, that 99.5% of those defects which we found were real defects. So we only have 0.5% in false positive defects, and most of those defects actually were related to the fasteners. So there was an issue that fasteners were breaking, that bolts were breaking, things were happening there, and due to this very frequent inspection, it was possible to keep up with the safety, to change those fasteners, to make new fasteners, to develop new fasteners, and actually in the end guarantee a safe infrastructure. The second case study here would be on the Elizabeth line in London. Again, this is a tunnel infrastructure. It's very good for inspection. It's 100 kilometers in total. 42 kilometers of this, again, in twin tunnels. And we're using a dedicated vehicle in order to do all those measurements. It's all slab track. And I think in this case, we not only have the visual inspection, but we also have the profile inspection and the geometry inspection of the system. Anyway, I would like to draw your attention again to the results of the visual inspection. We can see here, and this is something probably where this discussion hits that, okay, this could be something easy be detected or not detected by someone who's running along the tracks. And my conviction is that this type of defect is very difficult to find by people running along the track. In the upper image, for example, there is the clip in a perfect shape. So we see the toe, which is the small cap sitting on the clip. The clip is in perfect shape, and even the nylon insulator below the clip is in perfect shape. The second image almost looks the same. It's inverted, but also the toe cap is missing. So this is something when someone walks along the track, I'm totally convinced that this cannot be easily detected. And even more difficult to detect is the second example, which is the sleeper cracking. And sleeper cracking is, of course, something which is happening everywhere, and we know that all people dealing with sleepers or with slab track are very sensitive to this matter. But if we look at the images to the left, and this is probably what a human eye could detect while walking with perfect lighting, of course, along a tunnel track. And honestly, I don't see anything in those two images to the left. But when you zoom in and when you actually use the artificial intelligence to go into detail, on some specific items, you can actually see that the upper image shows a cracked sleeper. And this is the same image, just that on the left, you cannot see it. On the right, it's zoomed in, it's detected a crack. And this crack actually can also be measured, can be defined, determined how large it is, how long it is, how wide it is. A second, let's say, criticism of visual inspection is always that there are standard components which artificial intelligence might deal with, and then there's also a lot of non-standard components in railways. However, I think that a virtual inspection, a virtual walkthrough where the artificial intelligence tells you where there is non-standard components can help to do the inspection from the office. In this case, for example, you have this grid covering certain components in the track, switch components in this case, and for example, the inspection focus here is on this very small clip. That clip is very important in order to hold all the covers in place, and that would be something someone walking along the tracks would actually focus on. This is something, of course, the artificial intelligence could be trained to do if there is sufficient examples, and we have a group of annotation engineers just focusing on these very matters, but it's all depending on the number of cases you find. And these are very rare cases. So what the artificial intelligence would do here is just identify it as a non-specific or non-standard example, but a specific case. And in this specific case, this is brought to the attention of the person sitting in front of the screen analyzing the track. Jochen.
Yes.
I'd like to hand over to you.
One more for me. Yeah, just to introduce also the vehicles we're using for our one-stop shop offering. Here you see one of them, which is located in Austria, the point cloud. We're using, in our opinion, the largest system existing on the market to capture high-precision point clouds, which comes from Regal, which has the, what you see on the left side from me, right side from you now, 3 LiDAR scanners, 2 color cameras. It has all the DMI, the IMU, the GNSS integrated. Still, what is required to map the results then on the tracks, to have a real image of the tracks. And on top of that, we have a total fleet of 14 vehicles operating in Europe and US, equipped with such systems, but then also with the entire portfolio of sensors, part of it what Stefan introduced, but far more from the portfolio of DMA, like?
Yeah, let me allow to do some publicity in the end. We talked about visual inspection, about track geometry, but actually there's a lot of other systems Plaza Diagnostics is offering. There's turnouts and crossings measurements, a specific system which we developed for high-speed turnouts, full automation of high-speed turnouts. Of course, we do ray profile measurement. You saw a small example of that earlier, corrugation measurement, which is one issue that actually happens as well in slab-tracked situation, slab-tracked infrastructure. Third-rate power measurement, catenary wear and position measurement. The tunnel inspection, which is something you heard about from one of our competitors. Top of rail and rail web video inspection, it's something we looked at. The rail web we haven't spoken about, but of course this also includes the detection of the serial number of the rail, for example. We also have infrared and catenary video inspection and a couple of other solutions, as well as ultrasonics and eddy current solutions, which actually help to determine cracks and also find out about the defect depth in rail on the surface and within the rail down to the web. All these measurements, if possible, if physically possible, we can do with speeds up to 350 kilometers. On our own vehicles, we do it up to 160 kilometers, but I mean, we are not bound to our own vehicles. We also install systems on infrastructure serving vehicles, as you've seen before, for example, Elizabeth Line or Eurotunnel where it's not our own vehicles. Ultrasonic eddy current, of course, is systems which do not run at that speed. Also ground-penetrating radar is systems which run at lower speed, but all the other systems actually are almost unlimited in terms of speed. That was a bit of publicity to the end. Thank you very much. If you want to stay in touch, we are very happy to meet you later on at the dinner and tomorrow at the conference. Thank you.
So, any questions regarding topics explained during this session? I remember first risk management and then some question regarding defect detection, track survey and monitoring.
Yeah, hello, I think I have a question if I get right the name Giovanni. There was the ADT, Giuseppe, sorry. Okay, we know Giuseppe, but, okay.
Call me Joe, that's
Joe.
fine. Joe,
okay,
that's fine.
good. You were mentioning about the AI. Sorry, I'm not very specialized. I have no clue actually about it.
Not many
but
people.
what I want to ask, and it's always a question for me regarding AI and usage of AI, are you able to isolate the AI that is doing the study of certain database or whatever volume of information you have from cyber attacks? Because, for example, as a asset owner, yeah, you would like to not have any, let's say, wrong data. If somebody wants to play with that, it's possible to isolate.
This is an interesting aspect because as the AI has to be trained, it means that you have your own data set. And unless it is not poisoned, the data set, you are free. And the data set usually do not belong to the user. The user get the network built with the data set. So until we keep our data set in our server that is not connected to internet at all, and we produce the network, and the network we install to the system, also because the data set can be terabytes, while the network is a few megabytes. And it is quite difficult, if not impossible, to poison just the network. You need to poison the data set at the beginning.
Okay.
So from this point of view, when they say, oh, they can poison the AI and so on, it is not fully true if you keep the data set safe from any intrusion, let's say.
Okay, so practically the initial start, it's isolated and
Absolutely.
You work locally without, so AI doesn't need to be online to
Not actually.
think for you.
Not
Okay.
actually. I mean, in the learning process that I mentioned, we grab from the customer the new stuff, few images, 10 images, 120 images, whatever it is, with the human comment on that. Oh, this is like that, we would like to have this new kind of classification and so on. Then we get the images, we see, okay, good, bad, whatever, and then we put it on the data set of that customer. Because it's not true that the data set of a customer can fit for all the customers. This is also this we learned in time.
Yeah, lesson learned, yeah. Okay, thank you for that. And second question, I don't know, maybe you said, but I did not pick it up. What was the speed of recording of the trains running? What are the operating speed when you do this?
The speed is limited to the vehicle operation.
Okay.
Because, you know, line scan camera works on the tens of kilohertz. Of course, if you want 0.05 millimeters, then you have to go accordingly to the speed of camera, let's say 50 kilohertz. It is a a good camera, line scan camera, and then you cannot achieve the 0.05 at 1 or 200 whatever kilometer by hour.
Okay, so that will be in kilometers per hour around?
In kilometer per hour, so you can go to 300, but then you have a resolution, I don't know, of 1 millimeter per pixel, 2 millimeter per pixel. So if you want the crack of the top of the rail, maybe at 300 kilometers by hour, this is not feasible. From with the line, it is an easy game. You grab the line scan camera, you see the maximum frequency that they have, you have the maximum speed, and you get the
speed,
the step of the line scan camera that grabs the image.
Okay, thank you very much. This was it for you. Thank you. And one question for TMS, I think, if I noted well, about the point clouds. Scanning. Yes. When you do a scanning, I saw you put there a list of reference points. But are you linking the scanning to a primary network, or how do you know that the track is on the right position?
Because, so the way you measure track geometry, you have an inertial measurement system on the vehicle, which gives you a 3D space curve. And this 3D space curve is accurate, but because of the IMU drift, because of the GPS drift, it moves away.
And when you're in tunnel?
Then you put every 60 meters, because on every mask, you put a reference point where you correct this. That means then you have reference track geometry. And with the reference track geometry, you have a very precise, a fully precise representation of the movement of the tracks. And then you put this to coordinates. So these are the 3 steps we're doing. And when you have this, you have absolute track geometry, and then you map the point cloud on it.
Okay. So you have some reference points along the alignment, which they need to stay always there. And whenever you do the verification, then they always go back to that.
Quite simple markers. So it's a round marker with 4 reflection points, and the way we measure the distance is on stereometric. So 2 cameras with a stereo effect, 160 frames per second each camera, and out of this we calculate the distance.
Okay, thank you.
Sure.
Any other question there?
So I have a question to both ADT solution and Placer and Teurf with the cloud of points. So are your systems potentially capable to detect defects on isolated rail joints? So maybe ruptures on the rail or on the web, fish plates, bolts?
Yes, the limit has to be something visible. So something that has a visible evidence. In such case, first of all, we can have a first difference between what is good and what is not good. And this is easy, let's say. The more difficult is to classify what it is not good in the different kind of what it is not good. And so for each kind of different, let's say, error, you mean to have on your background a relevant data set on that. While for stating what it is good and what it is not good, you just need to have a relevant data set to describe what it is good. And when it is not enough matching the good, you say, okay, that is not good. Then it is a matter of classifying it. And yes, so whatever aspect that has a visible impact can be achieved.
Yeah, thank you very much for the question. I think insulated rail joints are known as one of the most critical components in the rail, which actually can cause rail derailation and so on. Actually, we have algorithms trained specifically for insulated rail joints. First of all, we recognize what is an insulated rail joint. This is quite easy to do because typically you have a number of bolts, similar on both sides, ideally. We recognize, as we actually said also on the clips example, for example, we actually differentiate the various components of the insulated rail joints. So we identify the bolts. We identify if the bolts are in place or if the bolts are missing. Also, I mean, like the bolt has two sides. If, for example, just the nut is missing on one side, we identify if the insulation layer is in place, if it's actually sticking out, if it's like missing, if it's fractured. From the top, we look at that. Of course, for the bolts and for the fish plates, we look at it from the side to understand if it's there. And then actually we check for the typical defects you have. So for example, like the crack that runs from the borehole to the upper side of the insulated, towards the insulated part. So this is all elements we check independently. And then we have a typical set of anomalies we're looking after. So typical borehole cracking we can identify, of course, only once it's beyond the fish plate, but also, like, let's say the elements which are there beforehand we can identify. Another element actually in regards to checking on insulated rail joints is what we typically do in combination with our track geometry system, because we can actually identify when the track is actually lowering once there is weight on it. And actually this is again what we see over time, what is changing over time. If you have an insulated rail joint which is straight over time and then it's actually getting lower and lower, then you can see that the joint is pumping towards, I mean not towards slab track typically, but towards ballasted track. And you can predict that it's either going, I mean continuing the deterioration with the same speed, or if it's a fast deterioration, then you can assume that there's, for example, a missing bolt or anything like this.
Okay. Thank you.
Well, I have to thank all the speakers and to thank you for your participation. I believe that today we had a very, very good opportunity to increase our knowledge about slab track technologies. I give you some information regarding today's dinner. Today's dinner by Fresco Trattoria at 8 o'clock. Remember to have the ticket. And for people who is in Holiday Inn Hotel, we meet at 7 o'clock in the lobby at zero stock. So this dinner is another opportunity. One scope of the union is to share knowledges, and that is what we have done today. But the second one is to connect people, and this dinner is a networking opportunity. Also, human factor is important. We are all working in the railway world, and it's important also this part of our job. And finally, I remember tomorrow we start at 9 o'clock. Thank you. Good evening in Napoli.
I travel all over the place, and I have decided